So in 2.4, we're going to talk about rates of change in tangent lines. So refreshing our memory a little bit, we're going to find the slope of the tangent line, and we're going to suspend what we know about the power rule at this point because we haven't learned it. So we're going to use the definition of the derivative and on the function f of x equals x squared at the point 2.4. So we're going to say the slope is going to be the limit as h goes to 0, and then we're going to take f of, and since our x value is 2, we're going to do 2 plus h minus f of 2 all over h. So here we're going to find the derivative. So this is essentially the derivative evaluated at 2. So we're going to take then the limit as h goes to 0 of 2 plus h squared minus 2 squared all over h. So that means we're going to take that limit as h goes to 0. We'll square out the 2 plus h and get the first one squared, twice the product, plus the second one squared, minus the 2 squared is 4 all over h. As usual, anything that doesn't have an h is going to cancel, and so what's left we can factor the h out of, and that'll leave us with 4 plus h. So that allows us to cancel that h, and then we can safely let the limit go to 0, which is going to make that be 4. So then our tangent line is going to be y minus 4 is equal to the slope 4 times x minus 2. So let's do a little different question. Instead of finding the derivative at a point, we will find just the derivative of a function, that is the derivative function. So the derivative of a function. So hopefully you remember this is going to be that f prime of x will equal the limit as h goes to 0 of f of x plus h minus f of x all over h. That's supposed to be an h. So you can sometimes, other books are usually more traditional, older maybe editions of calculus books, college calculus books might, instead of using the h notation, at one time it was more common to use the delta x notation. So this is really just the same thing, but it's written in the more, I don't know if I want to say archaic, but the older version of instead of h delta x. There's also what's known as our symmetric difference quotient. So our calculator uses a version of this when it is doing a numerical derivative. So it would be the limit as h goes to 0 of f of x plus h minus f of x minus h all over 2h. Of course, the danger there is you're never actually evaluating the function at the point where we're trying to take the derivative, and so sometimes you will misread it and try to take the derivative or get an answer to something where the derivative doesn't even exist. So the derivative at a point, we saw one version of that. That was the one we just did with the limit. To start with, the limit as h goes to 0 of f of a plus h minus f of a all over h. And the other version is the limit as h goes to 0. Let me say, that's not right. Limit as x approaches a of f of x minus f of a all over x minus a. Some books call that the alternative version of the derivative, alternative definition. So a reminder, it's been a little while, but a normal line, so what's known as the normal line, to a curve is the line perpendicular to the tangent line at the point of tangency. So the tangent line and the normal line share that same point where the tangent line intersects the curve. So for example, let's find an equation of the normal to the curve f of x equals 4 minus x squared at x equals 1. So first we're going to find the slope of the tangent line. So we will take the limit as h goes, let's do the alternative version because we haven't done an example. So I'm going to do this version right up here. So to find the slope, we can take the limit as x approaches a, which in our case is 1, and we want f of x minus f of 1 all over x minus 1. So in our case, the f of x is going to be 4 minus x squared. When we plug in 1, 4 minus 1 squared is 3. So go minus 3 all over x minus 1. And I should probably write my limits. So limit as x approaches 1. And that's going to be 1 minus x squared all over x minus 1. So that's going to be the limit as x approaches 1. We can factor that into 1 minus x, 1 plus x, the difference of two squares over the x minus 1. So the x minus 1, 1 minus x cancel, but they're going to leave a negative 1. So that is going to give us a negative 1 minus x. And we're going to take the limit as x approaches 1. So that's going to be a negative 2. So that is the same thing as saying our derivative of the function at x equals 1. Of course, we know the shortcut. So we know that the derivative of negative x squared is negative 2x. And if we plug in the positive 1 rather, we can see that that's going to be the same value. Then our point, if we plug in the 1, then I guess that's f of 1. So our point, whoops, that's supposed to be the eraser. So our point is going to have x coordinate 1, and 4 minus 1 is 3. So the tangent line would be slope negative 2, so our normal line is going to have slope positive 1/2, the negative reciprocal. So our normal line will be y minus 3 equals 1/2 times x minus 1. Okay, I'm going to move to a new panel here. And let's talk about, what can we do there? I'm going to do just a little bit of epsilon delta here, just to remind you. So we have said that the official or the Cauchy definition, so this is sometimes called the Cauchy after the French mathematician that lived in the 1700s, the definition of a limit. So the limit as x approaches c of f of x equals L, if and only if for every epsilon greater than 0, there exists delta also greater than 0, such that the absolute value of f of x minus L is less than epsilon for all absolute value of x minus c less than delta. So let's do just a quick example of one of these. So use our epsilon delta. We'll say show that the limit as x approaches 5 of, we'll say, x squared. And so we will plug in the 5 and see that that limit point is actually going to be 25. So now we know that this is our c, that is going to be our f of x, and this is going to be our L. So we will always start with the absolute value of f of x minus L less than epsilon, and our goal is to get to the absolute value of x minus c, which in our case is going to be 5, and we want that, and whatever we get is going to be our delta. So I'm going to leave the symbol epsilon in there, so our delta will be in terms of epsilon. So our f of x is going to be x squared minus our L is 25, and we want that less than epsilon. We can factor x minus 5, x plus 5. In absolute value is less than epsilon. We can split up our absolute value, and we would like to save the x minus 5 and get rid of the x plus 5, but we can't just divide by x plus 5 because for the wrong choice of x, that would be dividing by 0. So we remember that we're trying to take the limit as x goes to 5, so we're really only interested in values of x that are close to 5, and we're free to decide what we think is close to 5. And so I'm going to say for 4 less than x less than 6, then the absolute value of, and this x plus 5 I want to get rid of, so on the interval from 4 to 6, the biggest that x plus 5 can be is when x is 6, and that will make it 11. So then we can start a chain of inequalities. This absolute value of x minus 5 times the absolute value of x plus 5 must be less than, and I'm going to put the 11 in where the x plus 5 was. And this we're trying to make less than epsilon. So now that we've traded in our x plus 5 for the 11, we can now divide it to the other side, and we have found our delta. So again, remember what that's saying is, you can give me whatever you want for epsilon, anything as small as you want to make it. But my claim then is that if we choose whatever you chose for epsilon divided by 11, then all of the values of x within that delta on either side of x equals 5 will give us y values that will be within your epsilon of the limit L, which is 25. Okie doke.